Fermi's talents have also been concentrated on the search for dark matter, and in doing so it has observed unusual behavior in objects that remain unexplained. For instance, Fermi has discovered a gigantic structure in our galaxy, with what looks like bubbles extending above and below the galactic center. These are enormous gamma-ray emitting lobes. Each lobe is 25 light years tall, and the entire structure may be only a few million years old. Within these clouds, extremely energetic electrons are interacting with low-energy light to produce gamma rays, but no one knows the source of these electrons. When studying these massive objects, scientists must look at the other end of the size spectrum for answers. Those at CERN in Switzerland are expecting great things from the Large Hadron Collider, after it too received an upgrade, an increase of power by 40%. In its new improved form, it is due to produce far more data than it previously did. The LHC has already revealed the Higgs boson particle. One of two types of fundamental particle, fermions or the other, in our standard model of the universe. What other secrets might it be about to unearth, as it were?
With an increased luminosity, we gain sensitivity at the highest energy. So suddenly we will explore energies that hitherto were not really reachable. So if new physics is hidden there, this is the chance to see it. Some indications that created a lot of excitement with the theorists were seen with the experiment as there may be fluctuations, there may be real particles. As a physicist, of course, I hope that this is new physics already. But maybe that would be too simple.
The Higgs boson was the last puzzle piece in the standard model of fundamental particles and the forces which govern them throughout the universe.
What we really want is to understand the universe and why it looks and acts the way it does today. Our role as particle physicists are to figure out what the elementary particles are and how they fit together and interact, kind of like puzzle pieces, and the way the puzzle pieces fit together to give us a picture of the universe. Over the last 120 years or so, we've discovered all the individual puzzle pieces that build up to give us a theory called the Standard Model, which is kind of like the picture on the box. But we know that it's an incomplete theory. What we've essentially got is a small section of a puzzle picture that fits together very nicely and gives us all the particles that we see today, but we have no idea what the bigger picture is. The Higgs boson that we discovered in 2012 was the final piece in our Standard Model puzzle. And it was a fantastic discovery because it completed that small picture. And now what we can do is possibly use this Higgs boson to access the other parts of the puzzle. So our Higgs boson becomes like a Rosetta Stone to talk between the Standard Model particles and these new, what we call dark sector or hidden sector particles. So we're going to need to create many, many more Higgs bosons to be able to start seeing hints of this. And that's where the higher energy is useful. When we go to higher energy, it's almost as if we're getting a microscope to look on what we've discovered so far. It's possible that there are some very small differences in that Higgs boson, like the way that it decays, that we haven't noticed yet because we haven't had a strong enough microscope. But with a higher energy collider, with the LHC running at 13 TeV, maybe that is going to give us a strong enough microscope so we can see some small differences between our Standard Model theory and the Higgs boson that we have today. And maybe that'll give us some hint of some new physics that we can expect to come.
But it doesn't explain why nature prefers matter to antimatter, or what dark matter is. One theory that has been developed to answer these questions is what is called supersymmetry.
So one of the problems that supersymmetry could resolve is the mystery of dark matter. So this is something that astronomers and cosmologists tell us that there's an additional source of gravity in the universe which cannot be attributed to things we can see stars, the nebulae, and other things like that. And so at the moment, this has the mysterious name dark matter. I think that's at least partly because we don't really know what it is. It's quite reasonable to think that it's a particle of a kind that we could potentially produce at the LHC, and supersymmetry, or at least some forms of supersymmetry, could explain that matter and predict its properties. So the main problem, if you ask most physicists, I think, that supersymmetry would explain is the mass of the Higgs boson. With the Standard Model as it stands, we cannot explain why the Higgs boson has the mass it has. It should be many times heavier than it actually is. So heavy that we would have no chance at all of seeing it in any foreseeable experiment. And this currently has no explanation. Supersymmetry would provide a very neat solution to that problem, but it remains to be seen whether that's the correct solution or not.